Hello to everyone and welcome to KET Mathematics. In today's video, we are going to be focusing on FET and COT mathematics questions. But if you are writing any other concourse such as ANS, INSET, IUT, FASA, Public Works, SIPTIC, then this video is going to be very helpful to you because I am not just focused on giving the answers to these questions, but the concepts behind each of these questions will be explained to you in details. So I would advise you that if you are writing a different concourse apart from FET and COT, you can still watch the video till the end, and definitely you are going to get something that is going to help you in your own concourse. Now, this is actually the part 2 of the video series. I started with the part 1, which is the first 10 questions under this video series, and I'm going to put a link above here, and if you're interested, I will recommend that you should watch this video before you continue with the part 2, because it's simply a continuation of the first part. And I'm going to put a link also of this part 1 in the description box and also in the comment section. Okay, question 11 says that the integral of 3x divided by 1 plus x squared dx is. So in this case, we have been given our integral and we want to solve this. So the first step we need to do, there are two ways to go about it. The first method is we're going to use the substitution, and the second method is we're going to create and destroy. Now I'm going to solve using the two methods, and I'll prefer any student writing a concourse to go in for the second method. So the first method is substitution, which we're simply going to let u to be 1 plus x squared. In this case, then we are going to look for the derivative of this function with respect to x. So du all over dx will simply be, when we differentiate 1, we're going to get 0. Now when we differentiate x squared, we're going to get 2x. Now we want to make our dx subject. So if we make our dx subject, we are going to get dx will be equals to du divided by 2x. It will be du divided by 2x. So we're going to keep this somewhere very special. Now we also have to note that u is 1 plus x squared. So I simply go back to my original function and I do all the necessary substitution. So now going back to my function, I have that the integral of 3x divided by, I know that 1 plus x squared is u from here. So I'm going to have my u. Now I know that my dx is du from here, my dx is du, so it will be du divided by 2x. So I notice that I can actually cancel out x, so x can be cancelled, so I'll be left with just the integral. So this will be the same as the integral of 3 du divided by 2u. Now since 3 on 2 is a constant, then it can be sent out of the integral sign. So simply I'm going to write this as 3 divided by 2, the integral of du on u, and this is a standard integral, and the value of this will simply be the ln. So it will be 3 on 2, the ln of u plus a constant k. But we know that from star, our u is 1 plus x squared. So I'm simply going to have 3 on 2, the ln of 1 plus x squared. Now plus our constant of integration k. So looking at our answer, actually that's our answer. So looking at this answer, then our correct option will be D, be D. So D is the correct answer. Okay, now for method 2. Now for the second method, we are going to use the standard integral. We know the integral of 1 divided by x dx with respect to x. The answer is ln x. So basically, what does this mean? If we look at this in a simpler way, when we differentiate this function x, we are going to get 1. And since we are differentiating with respect to x and it gives us the numerator, so differentiating the denominator and gives us the numerator, our answer will simply be ln of the denominator. So the same thing will happen for 2x divided by x squared with respect to x here. So our answer will simply be ln of x squared. Now obviously plus a constant k, so even here plus k. So it's the same thing. When we differentiate the denominator, we're going to get the numerator. Therefore, our answer will simply be the ln of the denominator. So it is a standard formula. So we are going to try to create or make our function look either like the first one or the second one. So doing that, we are going to go about it like this. Now 3 is a constant. It can be sent out of the integral sign. So we'll be left with x divided by 1 plus x squared. Now I discovered that when I differentiate the denominator, I get 2x, because differentiating 1 I get 0, and differentiating x I get 2x. So I want 2x to be above here without actually changing the function. And to do that, we simply add a 2 here and we divide by a 2, so that the 2 can easily cancel back and nothing has changed. So now looking at this, if I'm differentiating now with respect to x, I'll see that the denominator now, differentiating the denominator, I get 2x, which is in the numerator. So this will simply be, the answer will simply be 3 all over 2, the ln of 1 plus x squared now plus k. So this method is much better than the first one. As you can see, there are 2 steps, and you know that when you're writing your concourse, time is a factor, and if you know how to manage your time, we are way above many people. So I'll prefer, and we'll have the same answer, which is 3 on 2 ln of that. Now for question 12, let me create some space here. Now for question 12 says, given that y is 1 plus 2x all that raised to the power a half, then dy on dx is. So here is another example in which we can use 2 methods in solving it. I'm also going to show you guys the 2 methods, and I'll show you which one is preferable and which one is shorter. So the first method we are going to use is substitution. So our substitution, we are going to do differentiation by the parametric differentiation. So we're going to use a substitution u to be equal to everything here. So u to be equal to 1 plus 2x. So differentiating our function u, our new function u, with respect to x, differentiating this our new function u with respect to x, we get 2. Now we're going to keep this aside. This is our equation star. Now we'll go back to the original function. We know that the original function will simply be y to be equal to u to the power a half. And this implies that when we want to differentiate now our function y with respect to u, then we're going to get from the standard definition of integration. So we simply bring down the power half, we copy the function and reduce the power by 1. So it will be a half minus 1. This is actually from the standard definition of differentiation. So doing that, we're going to get my dy all over du will simply be a half u to the power minus a half. Minus a half because a half minus 1 is minus a half. So we're going to keep this as our equation double star. So this will be our equation double star. Now, from the parametric differentiation, so we have dy all over dx can be written as dy all over du dot du all over dx. So looking at this, we haven't changed anything. We've just included a parameter which can easily be cancelled out. So we know our dy now on dx. Our dy on dx will simply be, what is our dy on du? From our equation double star here, our equation double star, we're going to have a half u to the power minus a half. And now our du on dx from equation star here, we're going to have 2. So looking at that, 2 can easily cancel, 2 cancel out. So we will be left with dy all over dx to be equal to u to the minus a half. But we know that our u was our u from here, our u is 1 plus 2x. So I'm going to have 1 plus 2x all that raised to the power minus a half. All that raised to the power minus a half. So we have that. So looking at that means the correct answer will be option B. So option B is the correct answer. Now I'm going to show you guys the second method. Now for the second method, we have been given this function. What we are going to do is we are going to apply the general formula for differentiation, but take into consideration that the function, because we know from the general formula for integration we have y to be equal to, if we have a function ax to the power n, then we're going to say the first derivative can also be written as a bar will simply be a n ax to the n minus 1. So this is the general formula. But in this case, we are going to take into consideration that our x here, the function x here, is not only to the raised to the power 1. What I mean is, like, it has something, like it has a coefficient. Yes, we have to take into consideration that maybe it has a coefficient and also a power. And to do that, let me explain that using this question. So the question says that we should look for the derivative of this function. Now, to look for the derivative, which is y bar, will simply be, I bring down the power from our standard differentiation formula. When I bring down the power, I have this. Now I'm going to differentiate the function because I'm considering that the function maybe has a coefficient, which it has a coefficient of 2, and also another constant. So when I differentiate the constant, I have 0. Now if I differentiate 2x, I'm going to get 2. So I've differentiated the function. I'm going to copy the function plus 2x, and now reduce the power by 1. So doing that, I see that my y bar will simply be, this 2 is going to cancel with this, so I'll be left with 1 plus 2x, all that raised to the minus a half, and this gives us an answer to be B. So this method is shorter. You see, it's 3 steps. In fact, it's 2 steps if you look at it well, because these are used in explaining. So you just have to master this part, the rule that guides the differentiation or the simplification of this function. That is, you bring down the function, you bring down the power, you differentiate the function, you copy the same function, and you reduce the power by 1. If you are able to always rephrase this sentence, every time you are faced with differentiation of this form, then you'll be able to solve any other differentiation. So our answer there is B. Now let's move on to the next question. The general solution of the differential equation cos x dx dy on dx equals to y sine x. So in this case, we are going to differentiate this implicitly, or we are going to separate our variables. So we are going to separate our variables since we are looking for since it's a differential equation and we want a general solution. So we know that we have cos x dy all over dx to be equals to y sine x. So we want to separate our variables. Now when I talk of separating variables, what I mean here is that we want to bring all the terms in x on one side and all the terms in y, or all the terms defined in terms of y on the other side. So in this case, I want to maybe if I want y to be on the left hand side and x to be on the right hand side, I'll start by multiplying all through by dx. So if I multiply all through by dx, I see that the dx in the denominator here will go away. So I'll be left with cos x dy to be equals to y sine x dx. Now I don't want cos x on the left hand side, I want it on the right hand side. I divide all through by cos x. So if I divide all through by cos x, I'm going to have cos x here and cos x here, cos x here. So cos x will be left with dy to be equal to y sine x divided by cos x. Now dx. I don't also want to see y on the right hand side. I want y on the left hand side. So I divide all through by y. So dividing now all through by y, I get dy all over y to be equals to sine x divided by cos x dx. So I've succeeded in separating my variables. So from here, I take my integral sign on both sides. Taking my integral sign, so I have the integral of this, so I'm integrating this and that. So as we saw in the previous example, the integral of dy on y will simply be the ln of y. So it will simply be ln of y to be equal to. Now, still I've explained a similar example in question 12 or 11. Here we have to look at this. When I differentiate my denominator cos x, when I differentiate cos x, I have negative sine x, but what is in the numerator is sine x. So I'll have to create a negative here and destroy it here. Why? Because if I take negative times negative, it will be positive, and we know multiplying in any number by positive 1 is still going to give that function or that number. So I've created this. So now when I differentiate the denominator cos x, I get negative sine x, which gives me the numerator. So here my answer will simply be minus, which is here you can even see it as minus 1. Nothing has changed. So it will give me minus the ln of cos of the denominator, the cos of the ln of the denominator, now plus a constant k. So that's our solution. So let's look at which option is correct. We have, so looking at this, we see that option D, I think option D is the correct answer. So this is our correct answer here. Now I'm going to question 14, which is 11. I think it's question. So moving on to the next question, we have this. So here we have been given this, and we're going to simplify this. So we're going to look for the conjugate of this function, and to look for the conjugate of a complex number, we're simply going to Looking for the conjugate of a complex number, we're simply going to multiply the top and the bottom by the conjugate of the denominator. In this case, we know our denominator is 1 minus 2i. So basically, we want to rationalize our complex number, and to rationalize it, we multiply top and bottom by the conjugate of the denominator. So the conjugate is simply gotten by changing the sign of the sign between the complex number in the denominator and multiplying the top and the bottom by it. So our denominator is 1 minus 2i. The conjugate of 1 minus 2i is 1 plus 2i. So we are going to expand our function here. So expanding this, we are going to have a 1, because 1 times 1 is 1. 1 times 2i, we are going to get 2i. And minus 1 times 1 minus I. And minus I times 2i will give us minus 2i squared. Now divided by 1 minus 2i and 1 plus 2i is actually a difference of 2 squared. So this will give us 1 minus 4i squared. But we know that I squared I squared is minus 1. So from the square root of minus 1, the basic definition of a complex number, the square root of minus 1 is equal to I. So from this definition, we see here that I squared will simply be minus 1. So here we are going to simplify our function by stating that we are going to have 1. 2i minus I will give us I. And now I squared is minus 1. So minus 1 times minus 2 gives us 2. Now divided by 1. Now I squared is minus 1. So multiplying by minus 4 gives us plus 4. So this will give us 3 plus I divided by 5. So breaking it down, we are going to have 3 divided by 5 plus I divided by 5. So looking at our options, we see that option A is the correct one. Option A is the correct answer. So we're going to have that as our solution. Now, question 18 says that given that y is equal to x ln, given that y is equal to x ln of 3x squared, the value of the y on the x when x is 1 is. So we have been given this function. There are also two methods in which we can solve this, but I'm going to show you guys the shortest method because we don't have time. Time is actually a factor, and I don't want the video to be very long. So I'm going to use, here we have been given a product. Let's say this is our function y to be equal to x ln of 3x squared. So this is our product. So we're going to consider this as u and as v, but we are not going to use the product rule in differentiating, because using the product rule will be very long. So I'll show you guys the other method, but basically the method will be using product rule, but it will be combined with the other methods that I showed you guys earlier. So this will actually be so y bar will simply be, we're going to keep one of this function u constant, and then we differentiate v, and then we keep now v constant, and then we differentiate u. So basically this is what we are going to do, but using a shorter method. So in this case now, our y bar will simply be, now if I keep my u constant, that is keeping x constant, now I want to differentiate this function. We know when differentiating let me demonstrate something down here. So if you have our function, let's say ln of f of x, right? Our function y to be equal to ln of f of x. This implies that y bar will simply be f prime of f of x divided by f of x. So that is the basic definition of differentiating logarithmic natural log functions. So in this case, we are going to differentiate 3x squared. So differentiating 3x squared, I get 6x Now I'll divide by the function itself from this definition down here. From this definition. So I'll divide by the function itself, 3x squared. Now plus, I'm going now to keep now v, which is this one, constant. So keeping that constant, it will be ln of 3x squared. But now I'm differentiating x. Differentiating x gives us 1. So nothing will actually change from there. So our answer, our final answer, y bar, will simply be equal to simplifying this, 3 can go here, 3 can go here, 2, and we see that our x squared, our x times x, so this will actually give us 1. This will give us 1 now, plus ln of 3x squared. But notice that the question said at the point x equal to 1, so we're simply going to substitute anywhere we see x, we will put 1. So our y bar will simply be 1 plus ln of 3, because 1 square is 1 and 1 times 3 will give us 3. So basically our y bar will just be 1 plus ln 3. And looking at our option, we see that the correct answer will be option C. Option C. So going to the next question, we have the modulus of the complex number. Now here we have been given a complex number and we have to look for the modulus. There are two ways in which you can go about this, but I'll show you guys the shortest method. But in the course of the video, I'll be showing you guys the other methods. But to make this video short, I'm going to use a short method. And please, if you find this video helpful, you can subscribe to my channel. You can also like the video in order to support the channel. Now, the easiest method is for you to look for the modulus of the numerator separately, look for the modulus of the denominator, and divide the two functions. So doing that, we are going to get, we know if we are given a complex number, let's say z2 equals to a plus bi, then the modulus of this complex number will simply be the square root of a squared plus b squared. So that will be the modulus. Now we're going to look at the denominator separately. So looking at the denominator, if we look for the modulus of this denominator, we're going to have 1 squared now plus the square root of 3 will give us the square of the square root of 3 will give us 3. So all that squared now divided by, now we're at the denominator. We were at the numerator before, now we're at the denominator. So the denominator says that we have 1 plus I. So the modulus of 1 plus I will simply be the square root of 1 squared plus 1 squared, which will be 2. So we have root 4 here divided by root 2. So this will simply be 2 divided by root 2. So that's our answer. Now, looking at that, option C will be our correct answer. Also, note that maybe the option, they might change the option C to be something like root 2 maybe, because if we multiply the top and the bottom by root 2, we haven't changed anything. So this just to demonstrate something. So we see that we are going to have root 2 times root 2 will give us 2. So these two cancel. So this will boil down to root 2. So in a different, maybe in a different year, they might instead come and put our the option of the correct answer to be root 2. And if you cannot do this manipulation, then you might be stuck. So it's always good to know this. So the last question, the complex number this can be expressed in the form a plus bi, where a and b are real numbers. As so here we are under complex numbers, and we're going to use the De Moivre's theorem in expressing this. So basically the De Moivre's theorem states that if you have a complex number, let's say z2 equals to let's say cos theta n plus I sine theta n plus I sine theta n, all that raised to the power let me say b, then this can be written as, this can also be written as cos b n theta plus I plus I sine bn theta sine bn theta sine bn theta. So basically we are going to apply that same rule here, and doing it correctly will be very simple. So now applying that, we're simply going to get our complex number to be cos of bringing down 9. We're going to have 9 pi divided by 27 now plus I sine of 9 pi divided by 27. So simplifying that, we are going to have if we 9 can go here, 9 can go here 3 times. So this can also be written as cos of pi on 3 plus I sine of pi on 3 sine of pi over 3. So we know cos pi on 3 is 60. So this will be cos 60 plus I sine 60. So doing that, we're going to get our cos 60. Our cos 60 will be a half now plus I. Our sine 60 is root 3 on 2. Will be root 3 on 2. Root 3 on 2. So looking at this, well, the correct answer will be option D. So option D is the correct answer. Okay, I think we are done for the part 2 of this video. Okay, thank you guys very much for watching till the end. Please, if you find the video helpful, you can please give me a like. If you want to see more content like this, you give me a follow too. You might subscribe to my channel, and you can put in the comment section, as I said earlier, if you want to see the part 3 of this video. You just write in the comment section like something like you are interested in seeing the part 3 of the video. So doing that is going to motivate me to work on the part 3 of the video and hopefully upload for you guys to watch. So thank you again for watching, and please don't forget to subscribe, you like, and you share with others, and see you in the next video.